In this video, I'm going to show the implementation of a simple list in C of integer type. And I'm going to do it like I do a number of the examples, and I'm going to build it up over a series of versions. So you can see here in the directory, I have V1, V2, V3, and each version just adds a little bit. So maybe it's easier to follow, or maybe when you go through it yourself, it's easier to see how it gets put together. So let's start by looking at version 1 of the list, which just defines the data structure. Okay, so in our C program, we have a header file that includes our IO library and our standard library. So it has a bunch of functions that you can look up that are common to most programs. And again, you're not linking to libraries here, you're including header files. The linking part happens at the linker phase after compilation. Okay, so I'm going to define using the struct type and the type def that I talked about with something called a list element. And so a list element is a structure which contains just one piece of data in the list. And a piece of data in the list is going to contain the integer, which we think of as really the list data, but also has to include a pointer to the neighbor. And so lists are structured, and there is the concept of ordering. And so you have somebody after you and somebody before you, unless you're the last or first element of the list, respectively, right? And so it's perfectly fine to have pointers to variables of type yourself within the definition of a data type. Yourself in this case is a struct list element. Okay, and we put the full structure definition here because we haven't yet type defed it until this point. And so we're just going to call this one piece of aggregate data a list element. All right, so it's a simple typical list implementation. You've no doubt seen other places. Typically, you'll get these already implemented for you in a modern computer language, but you can see we have to build them ourselves. Okay, and we're going to then define a list type, which is built off of a list element. Okay, and what is a list? A list is nothing other than the head of the list. And I include the tail also because it makes append operations order constant time. You don't have to do that, but I also include that. And I also include the size of the list. You can include other things, but basically a list is nothing really other than a pointer to its root element and some other convenience data that you carry along. And I'm going to call this data structure a list. Okay, so I created a new type of list. It's built off of a new type I created called a list element. And I'm going to use these to do standard list manipulation. And then I'll show you how to use it as a client in a main program. So let's look at version 2, where I do my first list operation. Okay, so I've opened up version 2, and the first list function that I'm going to implement is list create. You don't have to close that gap, but I like to. So the list create function, we think of it as like a constructor, okay, of this abstract type, but there's no such formalism within C, but we treat it as such. And the list create function, the way I've built it here is it returns a pointer to a list. Okay, when a person calls it, and it assumes that the list hasn't been initialized yet or memory has not been allocated for it. So you see in this implementation, I malloc memory for enough data to hold a list, right? Remember that includes pointers to the head and the tail and an integer for the list size, but the user doesn't have to know that. I set the head to null and the tail to null. That's a way of saying that there's no data in the list so far. And another way of saying it is the list size is 0, and I return a pointer to the list to the client. Okay, so if a client wants to create a list, the first thing they do is say list create. And now we're going to add some simple data to the list. First, we'll look at appends and prepends, and then we'll look at adding arbitrary data. Okay, so the next method is list append. It's going to require a little bit more work, but it's still easier than an arbitrary insertion. So this function takes a pointer to the list that was allocated by the list create function, and it takes the value that you want to append to the list. It just adds that value to the end of the list. Okay, so we're going to define 2 list pointers within this function, list element pointers. We're going to call them current and previous because we're going to need them to patch the list up as part of the insertion. So the first thing we do is this line right here, which it creates the new node. Remember, the nodes are list elements. So I'm going to malloc enough space for a new list element. And what I'm going to do, I'll slip this operation in here. I'm going to set the new list elements data to the value that I want to set the element to. Okay, now I've got to link everything properly. So I'm going to say the previous pointer is going to be the tail, right? Because now I've got a new tail, which comes after the old tail. So list.previous is going to be tail. the current node, which is the one I just inserted, its next pointer is going to be null because it's now at the end of the list. And the tail of the list, since this is the end of the list, is also going to be the same pointer. Okay, now I'm going to handle the special case that the list had 0 elements. If the list had 0 elements, that would mean the head is null, and that the head is also current, and the current node's previous element is null, indicating there's nothing before it. Otherwise, if it's not the head, I have to do the linking. So this previous that I created, I've got to set it as the current node that I just inserted, previous element. And then I have to set the previous element's next pointer to the current. Okay. So I should have mentioned explicitly, this is a doubly linked list. So we want to be able to traverse it forward and backward. And that's why for each node, we keep a pointer of the node before it and the node after it. And when we do that, we have to do a tiny bit more work. And it's all just being careful that anytime you do an insertion or a deletion, you sew the pieces back together correctly. And that just means setting the previous to next pointers correctly for the neighboring elements. Okay, so in version 4, I just implemented the prepend function, which follows the same reasoning as the append function. You just have to be careful, and you can just check that and make sure it makes sense to you. I show it right here, but I'm going to jump in version 5 to have a little fun. I wrote a list print function. So the list print function idea is you pass in a list, and it prints out the values of the list in some kind of sane way. And it's good for testing to make sure that these little functions that you implemented aren't buggy. And invariably, when you first program in C, they will be, but you can fix them quickly. And it's nice to have a little function like this, well, both for an end user of the list and also early, so you can do debugging. Okay, so to debug, I create a pointer to a list element, and I'm just going to put some brackets around it to make it look like a list. And so I'm going to just do a loop. So loop starts at the head of the list, okay, and as long as it's not null, it will print the data. This means print integer followed by a space of that element of the list, okay? And that will go back, it will check that, or it will set L equal to L.next, so it goes to the next neighbor. And then as long as it is not equal to null, it will print the data in that one and so forth. And this loop will continue until you get to the tail, which is null, or it will do nothing. If the list is empty, it will just print open bracket and close bracket. So once we do that, then we could say, well, what does this look like from the user perspective? So if you were a user, you just say, well, I'm going to create a list, a pointer to a list. Now you could make this pointer opaque and have it be part of the type def. We'll talk about that. In fact, I'll show a separate version of this where to the user it looks like this. And under the hood, it's a pointer, but you don't know that capital, that this variable list right here is really a pointer to a struct, right? It's hidden from you because it's built into the type def. Here, I didn't build it into the type def, so the user has to be aware that it's a pointer, a slightly lower level flavor, which C programs are used to, but you might prefer it to look more high level. So I'll type that up and I'll include that in the notes also. All right, but otherwise you just say list equals list create once you've created a variable type list pointer. Then let's say I prepend list 2000, prepend list 10. You notice this isn't object oriented, so can't do anything like that. I just have to build it into the name, and I have to make the struct the first argument. Okay, so I do some prepends, I do some appends, and well, if it all worked, I print it at the end, and if it all worked out, it would be whatever this says it would be. So we'll just do a sanity check, and I'll let you verify it's correct in your own time, and then we'll add the insertion and deletion functions. So we'll do GCC v5.c minus o v5. Too lazy to do the ANSI pedantic wall, and we'll just run v5, and boom. Well, I think that turns out to be what it should be after that sequence of prepends and appends, but certainly check me on it. Okay, now let's go implement a little bit more. So in this particular implementation, I'm going to do an index-based insert function. And there are different levels of abstraction in which you could do this. Some implementations require the node after which you want to insert the value as an argument to the insert method. That's a slightly lower level interface that assumes that you've already located the node, and insertion then becomes an order constant time operation. Here it's a order n operation where n is the number of elements in the list because I'm presenting it at a higher level, an index-based insertion. So say I want to insert after element index. The first step in that, first I do a check to make sure that index isn't beyond the end of the list. But once I do that check, I go right here and I say, well, I'm going to start at the beginning of the list at list.head and go either to the end or until I find the index of the list. So I'm going to count how many elements I've crossed in the list because I have no way, like with an array, of going directly to that index value. And so I just say if count equals index, then I found the index and I'm going to break from the loop. Okay, so what this means is that the element previous to the one that I want to insert it into is a pointer to that element is this prev pointer, right? So now I've got it. Once I've got it, I can do the machinery of insertion, right? So when I insert, I create the space for the new list element. I stick the data that I want to insert into the new list element. I set the previous pointer equal to the pointer I just found. And I set the next pointer to the one that was after the previous one because I'm slipping it in between the two, right? So I patch the list up properly. And then the one after previous is now the new one. And this is not going to pay for this code, but that's the idea. And there were sort of two things done in one there, so be careful. Some people layer this interface, but I just combine them because it's a little nicer. But the reason that you would layer it is because you'd want to expose an interface for each complexity, right? So there'd be an interface for insertion based off of having a pointer to the previous element, and then there'd be an interface to find the index of an element, and you'd sort of chain the two together. But not so worried about that detail. Now, when I remove an element, it's the same logic. And first I've got to find the address of the element, not the one before, but the actual index, I should say, of the element I want to remove. And then I link what's previous to it to what's after it. Okay, so I link what's after it to what's before it. So I basically just patch up the hole that I left. And then I call free on the element. It's very important to free any memory that you allocate. We didn't go into that into much detail, but it's very critical part of doing good C programming. It's something we'll talk about more. That's easy. The problem that we'll see is when the list contains pointers to allocated data structures. And you have to be very careful when you remove an element from the list to free not only the list element, but to recursively free all of the data that is pointed to by the node in the list element. Otherwise, you get a memory leak, right? So when we look at the abstract list, we will confront that issue. And then I have some other helper functions like return the value of the element at a certain index and clear all elements of the list. Okay, so I think these are things. Oh, and I added a few other things like find the first element that has a certain value associated with it. And I tested some of these functions in a longer main, and I won't dwell on the details. What I really wanted to show here is the basic principles for building a simple data structure in C and testing it, and also want to point out the limitations. And the key limitations are that these are just lists of integers. And so what I really want to move to and spend time on is how do we build a list of generic type? How do we build a list of, if you were in an object-oriented language, it'd say type object or some superclass type. Maybe it's more specific than object. That's what we really want to move to. Well, let's run a test on this real quick. Too lazy to type again, so I'll recall my other command and then I'll just edit it. Oops. Well, let's see. I think that's okay. I think I added that accidentally, and it's just a warning. So let's just go ahead and run. All right. And you can see when I cleared the list, it was clear. I asked what the index, the value of index 3 is. I did some insertions, some appending, and I checked it out and it looks fine, but you should not believe me. You should check it out yourself. Okay. And so that's kind of the spirit of it. So what I want to do in the next segments then is say, okay, those are the principles of list of integers. Let's talk about how we build more general type of list.